Welcome everyone. So this is another session on permanent magnet synchronous machine control, and today we are going to look at field weakening control of permanent magnet synchronous machines. Now, in one of the previous videos, we looked at DC machines that had a wound field, and we tried to study how the field weakening control works and what does it mean to achieve field weakening control, what kind of advantages do we get in being able to control. And we saw that we can extend the operating speeds to higher operating speeds by using field weakening control, and we looked at the constant torque region and the constant power region for a DC machine. Now today in this lecture we will look at similar concepts but applied to a permanent magnet synchronous machine and see how we can achieve that, achieve the same capability or extend the capability of synchronous machines through field weakening control. Okay, all right. So just to refresh, if you recall from the earlier video, in a permanent magnet machine, in case if we are to do field weakening control, we need to have two sets of windings. Typically, if you are looking at a permanent magnet DC motor, you will have magnets on the stator, and your armature, which is the rotor, has a set of windings, right? You see that there are windings on the rotor, and those rotor windings are connected to a commutator which maintains the current direction, or which adjusts the applied voltage polarity so that the magnetic field generated in the stator, in the rotor, is 90 degrees out of phase with the stator. Okay, we know that for torque generation in any machine, we try to maintain the phase difference between the rotor and the stator fluxes. Okay, if you recall this from our earlier videos, if this is your alignment, or if this is the direction your rotor flux, okay, if your rotor flux is pointing this way, we try to orient our stator flux to be 90 degrees out of phase in this way, so that we generate optimal torque, right? Now in a DC machine, this is mechanically achieved through the commutator. Because the commutator keeps changing the current at a certain point along the rotor, it will maintain that phase shift continuously, or almost close to 90 degrees. Okay. Now, in permanent magnet synchronous machines, we'll need to study that a little bit, because now we don't have control over the rotor magnets, right? We don't have control. However, because it's a three-phase machine, and once you transform that three-phase machine into a rotor reference frame, we have two voltage equations, if you recall. Okay, and let's actually go into those equations. All right, so if we look at the equations for the steady state equations for a permanent magnet synchronous machine, we see the following relationships. Okay, now saliency, we talked about saliency in a previous discussion. Saliency is basically the difference between LQ and LD. The inductance are different because the rotor architecture is designed in a certain way. The material is different, therefore the inductance tend to change. Now, given this, whether it's a salient or non-salient machine, if we look at this at the steady state voltage equations, we can see that the y-axis, which means it's directly along the flux. Okay, the d-axis is basically directly along the flux. If we are to let's try to draw a simple motor model. So if we have, let's say, an SM, PMSM, right? So you have a north and a south. So in this case, if this is the rotor, this is my rotor flux axis, rotor direct axis, D axis. Okay. Now, when we apply or when we generate currents using the stator, we try to generate the stator flux vector to be 90 degrees out of phase. Okay, which means we try to align the stator flux along the Q axis of the rotor. Okay, Q axis, quadrature axis of the rotor. Now, this way we guarantee this 90 degrees phase shift. Now, in this sense, if you look at these two equations, we have a voltage equation for D axis, we have a voltage equation for Q axis. All right. Now, when we say we are doing flux weakening control, that essentially means we are, let's say we are reducing the effective amount of flux along the D axis. Okay, we are technically diminishing the amount of flux in the D axis. Now, practically thinking of a machine, if it has permanent magnets, right? If we had permanent magnets, it's not clear how can we control that direct axis flux, right? So let me propose a couple of different control knobs that you can control. Okay, so we have two options. The goal is, if you remember from the DC machine discussion, we were able to reach higher speeds by controlling, by reducing the amount of flux. Because if you can reduce the back EMF constant, that means you have more voltage left to go to higher speed. Now, trying to follow the same concept, here, changing the direct in order to diminish lambda m in this case, or in order to change m, what we need to do is we need to introduce some form of negative flux, right? So if we can somehow generate some negative flux in this direction, so the total cumulative flux along direct axis will be lower, and which means our back EMF constant, so lambda m prime, the flux linkage constant, will be smaller. Okay, so that means we are able to apply or use the same voltage and reach higher speeds, because now you can increase omega r because your lambda m prime r decrease. Okay, all right. So in order to achieve that, what we need to do is we need to generate negative d-axis current. Okay, because this is the d-axis, this is where the flux is oriented. If we can generate negative d-axis instead of q-axis, so if you have q-axis current, it will result in a q-axis flux. If we generate d-axis current, we'll have more flux along the d-axis. Hopefully we are not saturating. If we have negative d-axis, we are basically reducing the amount of flux that's contributed along the d-axis, which is influencing lambda m prime r. Okay, so for the same IQ command, by introducing negative d-axis current, what we can do is we can reduce the effective lambda m prime r and be able to reach higher speeds. Now, so we talked about the d-axis current. Now let's look at the voltage equation. So this is just I'm rewriting the q-axis voltage equation here, right? And then we said, okay, by introducing negative d-axis current, we are able to change lambda m prime r, right? We are able to influence lambda m prime r a little bit, not a whole lot. We can change it a little bit, which gets us the opportunity to increase speed without changing the total voltage. However, we need to see another phenomena here. With negative d-axis current, depending on the speed that we are operating at, we are also able to contribute a little bit of voltage to the total voltage that is available to reach a higher speed. So there are two effects that we can see here. Okay, with negative d-axis current, we are increasing, we are adding voltage. Since this is a negative sign, negative becomes positive. Therefore, this total voltage will increase, as well as the flux linkage constant will decrease, enabling us to reach higher speeds for the same amount of voltage that we apply, assuming IQ is constant. Okay, so this is an interesting topic. This is something that you can investigate with a practical setup if you have a machine that you can experiment with, and depending on if you want to extend the operating speed for a brief period of time, you can use this technique to achieve higher speeds. Now, in order to do that, you are sacrificing current. Okay, so be careful when you are especially operating closer to the voltage limit. This might be difficult, and also you are sacrificing voltage, which means, in order to generate current, you need to apply voltage. That means you're kind of trading some voltage, which limits your total torque capability in order to achieve that higher speed. So you're still going to be looking at a torque speed curve that has this kind of a shape. Okay, so you have a certain point that you can operate at constant torque, and beyond that, if you want, so this is a rated speed, and beyond that, if you want to reach higher speeds, you will have to weaken the field, weaken the flux, which will allow you to reach higher speeds, but at the same time your torque is dropping. The highest or maximum torque you are able to reach is dropping because you have sacrificed voltage to weaken the field. Okay, so again, if this is not very straightforward, I recommend you to go look at the DC machine field weakening control, and then come back and revisit and look at the two equations that we have here to weaken the field and reach higher speeds. Okay, all right. So that's the end of the field weakening control part. Let me know if you have questions, concerns, or any clarifications needed on this topic. Thank you.